Okay, so what we have seen so far is that when we have our time-independent Schrödinger equation, and our Hamiltonian takes the form H0 plus some perturbation, right? This is the basis of perturbation theory. In the time-independent case, right, the Hamiltonian doesn't depend on time, and in the non-degenerate case, this just means that for each eigenenergy of H0, we only have one eigenstate, phi n 0. Then, if we substitute, if we consider that psi and En can be expressed as a power series in lambda, and we substitute this into our Hamiltonian, our time-independent Schrödinger equation, we get the following relation. This is a general relation, okay? This is valid for any k. Now, what we said was that this term is going to be equal to this term because the powers of lambda are equal. And I want to stop just a little, just for a minute here to explain what we're actually doing, because I feel like I didn't really go into much detail about why we're making each powers equal. Now, we saw after making this term and this term equal that the zeroth order correction was just really our original eigenstate equation, right? Our zeroth order correction to the energy is just our the eigenenergy of our original Hamiltonian, H0, and our eigenstate is just phi n naught, or 0. So, why are we making these two terms equal? Well, what we're saying is that if we have this expression, a0 plus a1 plus a2 lambda squared plus more higher order terms, and this is equal to b0 plus b1 lambda plus b2 lambda squared and so on. For this relation to hold for all lambda, in our case lambda is in 0, 1, we need that a0 is equal to b0, a1 equals to b1, and so on, so on, so on. A way to see this is if you take all of this to the other side, you get a0 minus b0 plus a1 minus b1 lambda plus a2 minus b2 lambda squared plus the same is equal to 0. For this to hold for all values of lambda, we need that this term is 0, this term is 0, this term is 0, and so on, so on, so on. So why do we need that exactly this term is 0? Maybe in some ways they could cancel out between each other. The thing is they can't, because if we are assuming that lambda, this holds for all values of lambda, the only way that this can happen in general is if the coefficients of lambda are all 0. Okay, so for this equation to hold for all values of lambda, I know I repeat myself, but it's important that we understand this concept. We need that all the coefficients are equal. So that's why whenever we have a power of lambda, this really is just lambda to the 0th power. That's why we say that this is the 0th order correction, where k is equal to 0, where k is the power of lambda. So for this to hold for all values of lambda, we need that each coefficient is equal. This is what we have done in the previous video. We made a0 equals to b0. In this case, this will be a0, this will be b0 because there's no lambda. Lambda is raised to 0th power. Now, in this expression, we have the rest of the powers of lambda, right? For k equals 1, we have something times lambda. For k equals 2, we have something times lambda squared, and so on. And here we have the same. For k equals 1, we have this term times lambda. For k equals 2, we have this term with k equals 2 times lambda squared, and so on. So, if we consider this and follow this reasoning again, we get that really all we have to do for this equation to hold, we already took care of the 0th order correction. We only need that this coefficient is equal to this coefficient. And this is what I have written here to save some time. So we have our time-independent Schrödinger equation. In general, the corrections are given by this relation. I have just taken this term here and put it here, and this term and put it here. So this is in general our relation. And if we know all the previous corrections, for example, we want to find the kth correction to the eigenstate and the eigenenergy. The only way that we can do it, following this method, which is the Rayleigh-Schrödinger method, it's the usual one, we need to know all the previous corrections. Okay? So let me just go to the first order and you'll see what I mean. So let me just erase this. Now, as I said, this relation is only valid for k equals to 1 or greater, because we already took care of the zeroth order. So, what happens when k equals 1? When k equals 1, this equation just becomes h naught times the first order correction plus hp times the k minus 1 is 0, that is the 0 order correction, and this, we're going to impose this exclamation mark just means imposing the equality. The sum going from L equals 0 to 1 of EL En, and K, what is K? K is 1, so it's just 1 minus L N. And this will, if we expand the sum, we get the 0th order correction times the first order correction to the wave state plus En1 and the 0th order correction. Now, from this, we can do various things. We can first just group the first, right, the first order correction to the wave state and the 0th order correction to the wave state. But before we do that, I feel like it's easier if we straight away take care of how we are gonna tackle the first order correction. Okay, so what I mean is that, let me just put this order 1, that we are gonna be doing the general method in order to find E1, the first order correction to energy, and the eigenstate. What we usually do is we take the inner product with some arbitrary element of our basis. So what do I mean with this? What I'm going to do on both sides of this equation is to take the inner product with the bra 0L, where L is really any value, it's an arbitrary element of our basis. So if I do this on both sides of the equation, I just have my Lth element and H naught, my first correction to the energy, sorry, to the state, plus again the inner product with HP, the 0th order correction. But wait a minute, we know the 0th order correction we derived it before is just phi 0n. So this is what I mean when I say that whenever we want to find the order of k, we need the previous orders. That is, to find k equals 1, we need to know what k equals 0 is. To find k equals 2, we know k equals 1, we have to know k equals 1, k equals 0, and so on, for higher orders. So this, it's the last time I'm gonna write this exclamation mark, because we already know that this is an imposition. This is just, well, the 0th order correction is just 0, so I'm gonna take out the parentheses, just meaning that this is the 0th order correction, and this is just the eigenstate of H naught. But as we saw, they're really the same, but this is your notation. So psi 1n plus the first order correction to the energy. Oh, sorry, we are taking the inner product. Yes. So we're taking the inner product, 0L En0, first order correction, plus this. Okay. Again, the 0th order correction, which is this one, is just phi 0. So we write phi 0n. Now, we're already working with this in order to find our corrections to the eigenstate and the eigenenergy. There are two distinct cases here. The one where L equals n, in this case, this inner product will not be 0, and when L is not equal to n, in this case, it will be 0. So what do I mean? What we're going to be doing is first to consider L equals to 0 to n. But before we do that, I want to write an expression okay, for this. And here I'm gonna put a gamma. And what I mean with this gamma, I'm just taking this term here. What I mean with this gamma is that we do not care what is on this side. It can be any eigenstate. And you'll see why. If we have this relation, well, we can just rewrite it as if we call, okay, if we apply h0 to gamma, we can call this alpha. It's another wave function or another element for Hilbert space. So we have this. But we know this property. Where is it? That when we have a dot product and we take the complex conjugate, we can just invert the order. So let me just put it like this. So when we have this is the same as the complex conjugate of the reversed order. So, but what is the bra of alpha? Well, it is just gamma, the bra of gamma, and h0 dagger times, well, of course, COL and the complex conjugate. But we know that h0, which is about Hamiltonian, it is self-adjoint. That is, its dagger is equal to h0. And just for context, a dagger is the adjoint of an operator, and if it is expressed in matrix form, it's just the complex conjugate and the transpose of the matrix representing the operator. So what we have is, well, if h0 dagger is equal to h0, well, we can just rewrite this as gamma h0 to L. But because we know what h0 times any phi 0 n is, we can just express this as gamma EL, because we have an L instead of an N, of this. And taking the complex conjugate, we can reverse the order. Then this comes out, it is a real number, the energy. So we get, and it is a real number because, as we will say in other videos theory, the eigenstates of Hamiltonian have to be real, eigenvalues. Yes, and we take the reverse order. So this is what we have this expression. We can rewrite it as the energy times the inner product between these two states. This is like saying formally that we are taking this. We're taking this one with this one, and we just get the eigenenergy and the bra. So, where am I going to write this? Let me just write it here. Because this expression is going to be extremely useful in all our calculations, really. In general, this is what we're going to be using. So, if we have COL H0 gamma, this is the same as the energy times the inner product with gamma. Really important relation and not too hard to derive. So now that we let me just raise this a little bit. Now that we have this relation, we can rewrite this using this result, where gamma is just the first correction to the eigenstate. So we get the Lth energy of H0 and this dot product. So again, gamma is just first correction to the eigenstate. This one, we can't really do anything in this one. We cannot follow the same procedure because we don't know how, we really don't know, we haven't specified what HP is, so we'll just leave it like that. We don't know how HP acts on anything. So in general, we will just leave it like this. Just put this P. Now this has to be equal to these two dot products, but this is a constant, so we can come out of the inner product, because in general, the inner products are integrals and they are inner operators, so we can take it out. So let En0 L phi 1 n psi 1 n. plus with the same reason here. Okay, now I just wanted to remember that we said that that the first order correction to the eigenenergy, eigenstate, I always confuse with the names, is an element of our Hilbert space, and we have our basis in our Hilbert space, so we can express it as a linear combination of our basis elements. So we get from n equals to 0 to positive infinity of Cm and our elements of our basis. Now, when we take the inner product with phi 0 L, assuming this is a convergence series and everything, and it's a linear operator, so we can take the inner product on both sides, and the inner product can go inside, so what we get is Cm times this. But hey, this is an orthonormal basis. This is just our Kronecker delta. So we get that the only terms that are not 0 are the ones where m equals to L. So L equals to m. Otherwise, everything will be 0 because the two basis elements are orthogonal. So we get Cl. I'm going to write a 1 here to indicate that it is the coefficient of the first order correction to the wave state. 1 times, well, this dot product. But this is just 1 because it is the same answer. So we get that the inner product with the basis element is just the coefficient Cl. So here, instead of writing this, we can just write Cl, right? This is just the coefficient Cl1. And likewise, we get the same thing here. Now we can reorganize this. Actually, let me just put it here. Because these two terms are equal, we can just take the energy to this side and write EL0 minus EN0 times this inner product, which is just the Cl1, plus this term, which we cannot really simplify any further, and this is equal to this one, the first energy correction. So this equation involves Cl and En1. What we really want to find is this coefficient and this energy correction. So how do we do it? So I said we are going to assume that L equals to N and that L is not equal to N. So if L equals to 1, we're just multiplying, we're taking the inner product with phi n. In that case, this is equal to this. So we get En minus En00 Cl1, Cn, sorry. So this would be 0. So hey, it doesn't matter what the value of Cn is, this equation is always going to hold. So we cannot, I repeat, we cannot determine Cn from this equation. So Cn1 is still undetermined. And we'll see later on how to determine it. But we cannot determine it because it's not going to appear in our equations. And likewise, if we make L is not equal to N, it's also not going to appear because instead of Cn, we'll have the other term, Cl. So this is something to have into account. Now we're going to be able to find all the coefficients except Cn. Now, here we just take this inner product, Cn Hp by 0n, and because this is an n, take the inner product, it just becomes 1, so we get this. So we have determined our first order correction to the energy. It is just this expression. And just recall that if we define we know that expectation value in this state is just this inner product. So our first order correction to the energy is just expectation value of HP. This is a very important result, and as we'll see in examples and in the applications, it's really useful to calculate corrections to the energy, and it's not too hard. Okay, so for now, I'm also gonna say that Cn1 is equal to question mark because we have not been able to determine it from this equation. Spoiler alert, we will determine it afterwards with the normalization condition of our eigenfunction. We'll see later on. Okay, so now if we consider the L different from n case, we get that this is no longer 0. This just is the same, we cannot simplify it any further, and this becomes 0 because these two are orthonormal to each other. So what we get is that, yes, we get this. Now again, just this CL1 is just the coefficient of the first order correction. We can take this to the other side and just write this. HP and 0, and we are going to divide both sides by this quantity. So I'm going to erase this and write it here. If we distribute the minus sign, we can change the order and we get this. This is the coefficients of our eigenstate, our first order correction to the eigenstate. Notice that this doesn't blow up to infinity because L is not equal to n. So as we said before, we have determined all the coefficients except Cn. So that's why I wrote here a Cn equals to a question mark, because we will not be able to determine it now. We'll determine it afterwards. Depends on the normalization that we get, that we choose, but we'll see how we get that. So what else? So what this means is that the first order correction is the sum over all m. Okay, just remember that when we have our basis elements, phi m, m can, depending on the Hamiltonian, can be 0, 1, 2, 3, go to infinity, or it can have some other numeration. So in general, we don't know how we have named or numerated our terms of the basis, so we just write m, the sum over all m of this. CL1, and well, let me just write L, just to not get confused. We're summing over L. 0 L. Now, this is the same as this one, so we can just rewrite it. And I just want you to understand just one thing. It's just for to make things more comfortable in the future. Instead of L, I'm gonna write M. Okay, this is just a dummy variable, so I'm gonna write M because we're gonna be using the letter L. We have been using it for this summation, so I'm just gonna write M. But this is just the same expression. So if we sum over all n, we notice that there's a problem at m equals n. This goes up to infinity. So our Cn cannot really be this, have this form. But this is no problem because we already said that L is not equal to m. So really, we are summing over all of this with the condition that n is never equal to n. So this would be our first order correction to the eigenstate. Again, to find Cn, we need another equation, which is the normalization equation that we'll get on with afterwards. So let me just copy this result here, and we'll get on with the second order corrections to the energy and the eigenstates.